All right, so we're calculating the maximum capacity of a beam when rho is equal to rho max, and sometimes we can't change the dimensions for lots of reasons. So we're going to compute that maximum capacity. Rho max means the steel yields. We're at 0.9 as our phi factor. Calculate the area of steel from the definition of rho, and what do we get? 0.73? 1.73 square inches. And if we then, everything else will fall out. A is equal to AS F sub y over 0.85 F prime CB, which is 1.73 multiplied by 60, all divided by 0.85 F prime CB. This is 4, this is 6. And what does that come out to be? Times 10 5.09? 5.09 inches. Our moment capacity is, I'm sorry? Yeah, sorry. Moment capacity, phi m sub n, which is 0.9 multiplied by ASFY d minus a over 2. If we do that, we can calculate, let's see, 5.09 over 2 equals that. I'm going to multiply this by 1 foot divided by 12 inches. I get 104.7 kip feet. Anyone else got the same number? Different number? And so if that's our case, that is the maximum capacity we can get out of this beam. Well, that's not very good, right? We can go back and calculate that maximum moment capacity if we have our beam and it's simply supported. And let's have it span, what's a reasonable span? 30 feet. And we'll just check a distributed load. The moment from that distributed load is WL squared over 8. So if the moment, and that's equal to 104.7 kip feet, and this gives me that W is equal to 104.7 multiplied by 8 and divided by 30 squared. What's my allowable load in pounds per linear foot? Multiplied by 8 equals over 30 squared. That's not a very big capacity. If you figure that's, let's say that's 40 feet this direction. 40 feet times 1 foot width is 40 square feet multiplied by 50 pounds per square foot is 2,000. And cutting it in half, because half of it sheds the load this way, this beam has a requirement, unfactored, of 100, or sort of 1 kip per linear foot dead load. It's inadequate. So now we have a problem. If the W requirement is greater than 930, no beam exists that meets the code. And is 6 inches by 18 inches nominal size. That's a problem. Because very often we're going to find out, I mean, you can imagine if I tell the architect, hey, no problem, drop a line of columns down the center of this building, or center of this room. Now, L is cut in half, and I square it, so the load is cut by fourths. So that might not be efficient. Just put just a single line of columns. What's the architect going to say? When I was working with my muse and how people would feel when they were in this building, those lines of columns are like daggers into my muse's heart. You can't do that. So fine, I'll make the build beams deeper or wider. Oh, you can't do that either, right? Can you imagine if I have this this masonry wall, right? And I build it with 6-inch masonry units, except the beam is 20 inches up above, and it's not, there's no false ceiling. It looks like, well, that's weird. Why is that there? And since our moment of inertia is going to vary with only with the width and not with the cube of the depth is way more efficient. In fact, moving it this way, widening the beam only increases our value of B. That doesn't help our lever arm. We want to deepen the beams all the time to increase their capacity. So what if we can't do that? So the architect says, well, Kevin, you know, I'm being recorded, so I would not use the exact words that they would use. They would say, my muse is bleeding and stabbing, and from your stabbing, you can't have any columns there. You have to find another way to me to realize the vision of my building. So I say to the architect, that's fine. I'm going to do that because engineering is about solving the problems other people create to think that the world's a nice place to live in. I'm going to build 2 beams. I'm going to build one beam out of reinforced concrete and steel. I'm going to use it to row max, to its maximum limits. Then I'm going to build another beam that's 2 bars in the compression zone and 2 bars in the tension zone and nothing else. And that's going to work because I'm going to put those 2 beams physically in the same place. I'm going to take 2 beams. I'm going to take this beam that I just analyzed here, right, where this is this has a reinforcement ratio is rho max, right, AS over BD. This is AS, this is B, this is D, and I'm going to add to that this beam here. This is going to be A2S, and this is going to be A prime S, because it's in compression. And I'm going to build these 2 beams physically in the same place. So I'm going to end up with a beam that's still 6 by 18. That's really behaving like 2 beams in the same space. Take that, Mr. Architect. You can't tell that I did it. And I'm going to have the same conditions. I'm going to make sure my beam stays in tension control because I'm not a maniac. And I'm going to design these 2 beams independent of one another, which is going to give me a terrific increase in capacity And these are called doubly reinforced beams, as opposed to singly reinforced. Some people say, oh, it's because you have a single layer, but I could have more than one layer. Doubly reinforced beams means I'm reinforcing it with steel in tension and steel in compression. Because this bar, these bars up here, this steel, is in compression. And remember, we have concrete, right? It's bipolar. Compression is like happy storytime lady. When she's happy, she's really, really happy. And when she's not happy, she's not happy. Concrete is bipolar. In compression, strong. In tension, sucks. But steel's constant. They may give me a compressive strain, give me a tensile strain. It doesn't matter. Up until the yield point, till the yield stress, I'm elastic. After that, I'll yield. And I'll yield in compression, and I'll yield in tension. Tension's easier for us to imagine. But the steel will yield in compression the same way. That's what we're going to do over the next several, at least 2 weeks. We're going to learn how to analyze doubly reinforced beams. And it sounds complicated, right? But remember when we started flexural beams, we were doing singly reinforced, and I said, just stick with me for a little while, and you'll catch it up. Do you feel comfortable doing singly reinforced beams now? Right? Do you know what row min, row max, all those things are? In 2 weeks, you're going to be able to look at a beam and say, oh, yeah, that's doubly reinforced. And because it's doubly reinforced, I know how to analyze it. It's all going to be the same sort of thing. I'm going to draw some triangles. It'll just be like the good old days. If you look at a reinforced concrete beam, when we're done flexural analysis, because flexural is analysis, we're going to look at shear. Shear forces, right, cutting forces, they're handled in a mechanistic way. In other words, we just say, this is how it's going to work, and there is no analysis. There's either you have the right amount of steel or you don't. You either need steel or you don't. Very easy. So we don't teach them as analysis and then design. But flexural is way more complicated. The way we're going to resist shear forces is we're going to build our beams so that bars will sit in this orientation in the beam. And when the shear comes to tear it apart, it's got to shear the concrete, which has shear strength. And it has to shear through this steel. Now, if I go to build a beam, what's the easiest way to keep this in the right location? I'm going to put tension reinforcement down here. Put a couple of bars up there. Now I can tie this steel together, stirrup, top bars and bottom bars, over there with crew number 1. And crew number 2 can put up the forms for the beams 35, 50, 200 feet away. And then I can take the tied together beam, pick it up with a crane, swing it in place, and put it in the forms. Now you're taking scheduling. Rather than doing erect the forms, tie the steel, I do erect the forms and tie the steel and marry them together at the end. Right? Makes it easier to construct. Sometimes when you do a singly reinforced beam, you still put bars up here, you just don't account for them. That's wasteful. So almost always we'll see doubly reinforced beams. And you need to know how to analyze them. And it's all simple. We're going to derive all of this starting from the steel has these properties, concrete has these properties, and strains and therefore stresses are distributed linearly. But we don't have time to start that today. As much as I would love to continue, we've covered a pretty important concept, which is reinforcement ratio. And we will, now that we have it, we'll find it's really useful in analysis of doubly reinforced beams. Anybody having any issues with their homework? Everything's been turned in for the most part. So you're probably out of assignments. Just have to give you an assignment.
We just have that one so far, right?
Yeah, you want to do 4 or 5 beams, like given these beams, determine if they're adequate. Might be, is this beam adequate if the imposed moment is 100 kip feet or whatever the heck it is? You just go back and if that's the last check, right? It's the beam's adequate, but if you don't have the capacity, then it's not adequate anymore. All right? What's your preference for an examination? In here or not in here? In here or online? The advantage of in here is I can mark it immediately.
How would it be online though?
What's that?
Like online wise, would it be like kind of like how the homework is?
Yeah.
You do it on paper and then submit it?
And I'll put it out to a little, I think I can figure out how to do a vote. The advantage is that you quickly get feedback. The disadvantage is that we lose a week. I don't know if we want to lose a week since we're doing it this way. But let me think about it. If anybody has a strong preference, send me an email. Have fun on the weekend. Do you have in your monastic cell where you're going to spend the entire weekend? Do you have windows?
Yes.
So you want to tape those over. This is a piece of advice.
No, I already got like a shade over it because I don't want to see kids outside.
Exactly. People who are taking, we used to see people who are taking sociology and psychology, sitting in on blankets, looking up at the sky, saying, "I'm so busy." Yeah, those were great people.